Hello everyone, welcome to lesson 5.4. I'm clearly wearing the same clothes as lesson 5.3, so either I did not change or I'm doing two films in one day. You can figure that out on your own. Anyways, here's your objective. I will be able to write positive and negative fractions as decimals. Basically, this is the same thing as the Hartwell method. I know the Hartwell method is not a real thing. We just made that up because Ms. Hartwell taught me how to teach math one day. But if you have, let's say, 3 over 5, 3/5, that's your fraction. How do you turn it into a decimal? Well, it's simply 3 divided by 5. So it's 3 divided by 5. And then we're going to turn it into a decimal because 5 can't go into 3. So I'm going to have to annex some zeros. But 5 can go into 30. How many times? 5, 10, 15, 20, 25, 30. It can go in 6 times. So I bring my decimal up, and 6 times 5 is 30. So I have no more remainder. I don't have any more decimals to add on. I'm done. So 3/5 as a decimal is 6/10. All right, the Hartwell method is basically what we're doing today. But we need to know a little bit of vocabulary before we move on. Here's some vocabulary to know. We have to know about rational numbers, terminating decimal, sounds kind of rough there, and repeating decimal. First of all, a rational number is any number that could be written as a fraction. So the number 4 is not a rational number because, well, actually, no, sorry, it is. Yeah, because 4 can be written as a fraction, can it? So here are two examples. 3/10 and 5/6 are both rational numbers because they're written as fractions. All right, a terminating decimal, a decimal that stops. Well, there's that 3/10 again. If I do 3 divided by 10, how many times could 10 go into 3? Well, it can't, so I need to annex some zeros right there, and I bring my decimal up. 10 goes into 30 3 times. 3 times 10 is 30. I have nothing left. I'm done. It's terminated. There's no more place value spots after the tenths. There's no hundredths. There's no thousandths. It just cuts off. So a terminating decimal is one that stops. I bet you can figure out what a repeating decimal is. It's a decimal that never ends because it repeats itself. It just never stops. For example, if I were to divide 5 divided by 6, that example for my rational number, I would get 0.8333333333333, and I can keep going if I want to because it'll never end. All right, a decimal that never ends is a repeating decimal. All right, so our first example we have right now is to write 5/12 as a decimal. Okay, just like the Hartwell method, we take 5 and we divide it by 12. And I already have this example listed for you. How many times can 12 go into 5? Well, it can't. So I annex a 0, and I put my decimal in there. 12 can go into 50 4 times. 4 times 12 is 48. I minus 48 from 50, and I get 2. And then I have to annex another 0 and bring it down. How many times can 12 go into 20? Well, it can go in once. There's my 1. And 20 minus 12 equals 8. Annex my other 0. There it is. How many times could 12 go into 80? It can go in 6 times. 6 times 12 is 72. And look what happens here. You can start to see that there's going to be a repeating decimal because 80 minus 72 is 80. Then 80 minus 72 is 80. And I can keep going, but I don't have any room over here. I can annex more zeros if I want to and keep writing 6s and keep going, but I could stop once I have a repeating decimal. So my answer is I'm not going to write 0.41666666. I'm going to use something called bar notation. If the 6 is repeating, this bar over the 6 is my signal that the 6 is going to repeat. So I know that the 6 will go on forever. Notice that the bar is not on top of the 4 or the 1 because the 4 and the 1 do not repeat themselves. The answer is 0.416666666666. It's not 0.416416. So it's important that my bar is only over the 6, only the number that's going to be repeating. Now, same kind of deal when you're working with negative numbers. It says write negative, I hope you can see the negative sign, negative 2/9 as a decimal. What you're going to do here is you're going to do 2 divided by 9. There's my 2 divided by 9. Now I did the whole problem for you again ahead of time. But I'm going to forget about the negative sign when I'm working with this. But it's important that I add my negative sign in at the end. So once again, 9 can't go into 2, so I annex a 0. 9, 18, it can go in 2 times. 20 minus 18 equals 2. And as you can see, when I annex another 0, I'm going into 20 again. So it's going to be 9 into 20 again. 9 times 2 is 18. There it is. I can keep going on and on forever, but that would be a waste of my time. So in fact, I should have stopped earlier, and that's why my answer is just negative 2/10 repeating, because there will be infinite 2's that never stop. You don't have all day for that. No one has time for that. That's why you put your bar notation on top. Alright, so this one I didn't do ahead of time. I'm going to actually do it for you so you could see what to do here. Now we have a negative number and it is a mixed number, and we can't deal with mixed numbers as you learned in the last unit. We have to make an improper fraction. So once again, I'm going to forget about the negative sign until the end. If it's negative, it's going to be negative at the end, okay, when I turn it to decimal. So 6 times 2 equals 12 plus 1 equals 13. So as a fraction, I have 13 over 6, which is basically 13 divided by 6. Now it is negative, so I'll put my negative sign there to remind myself. At the end, I got to put it back. So I have 13 divided by 6. Okay, 13 divided by 6. Okay, here we go. How many times can 6 go into 13? 6, 12. All right, so it goes in twice, and 6 times 2 is 12. So 13 minus 12 equals 1. So I have to annex a 0 here. All right, and I'm going to bring my decimal up here as well. Notice that I'm going to have 2 point something because I had a 2 over here. All right, that's why I have 2 point something up there. How many times could 6 go into 10? Well, it can only go in once. 1 times 6 is 6. 10 minus 6 equals 4. All right, 6 can't go into 4, so I have to annex another 0. How many times could 6 go into 40? 6, 12, 18, 24, 30, 36. It goes in 6 times, and 6 times 6 is 36. Man, we got a long one going here. 40 minus 36 equals 4, and 6 can't go into 4, so I have to annex another 0. Bring it down, up. I'm starting to see that it's going to repeat here. There's my 40. I have another 40. 6 can go into 40 6 times again. All right, and then 6 times 6 is 36. And I'm going to stop now because, once again, I'm going to get 40 minus 36 equals 4. And it's going to be another 40. And I'm going to keep going with 6, 6, 6, 6 on forever. So I could stop right there and realize that's going to be 2.16 repeating. The 6 repeating. But can't forget that it was negative as well. So my answer is negative 2.16 repeating of the 6. All right, negative 2 and 1/10, and then 6 hundredths that are never going to stop repeating. There'll be 6 thousandths, 10 thousandths, and so on and so forth. So this is my final answer and what it should look like. Okay? All right, you guys have some work to do. Let me erase all this hubbub up here. You have 3 problems. You have to turn each fraction into a decimal. Use bar notation if necessary. So if it repeats itself, don't sit there all night writing the same numbers over and again. Put a bar on top of it, and it'll repeat. That's your repeating sign. So you have 7 over 9. Think of it as the Hartwell method. 7 divided by 9. I'll even start you on this first one. 7 divided by 9. Okay? Number 2, negative 1 over 33. I'll even start you on this one as well. 1 divided by 33. 1 divided by 33. And don't forget it is negative to put your negative number at the end. Number 3, you're all on your own. I'll give you a little hint. Don't forget to turn this into an improper fraction. We can't deal with mixed numbers. All right, good luck, and I will see you when I see you. Goodbye.